So good afternoon, everybody. So thanks for joining. I can still see some people are joining as we're speaking. So just a few introductory words. So yeah, these are just some seminars, row seminars that we organize online every now and then, roughly every month, and try to just disseminate some of the work and research that is happening around Pavia online while we're still waiting to get back into the classroom and into offices. So today's seminar is going to be roughly 1 hour. So the idea is to stay within 1 hour of duration. The structure will essentially be the presentation and some questions afterwards. So we should have some time just for questions and clarifications. I would just ask everybody to keep their cameras and microphones off. Cameras on if you wish, but the microphones off so that we don't have any interference with the presentation. And just to note that I'm recording this right now, so the plan will be to upload the presentation onto YouTube afterwards, so it will be available for anybody who wants to go back and check again or share with anybody who didn't see it. So links to those will be in on the LinkedIn page or on the emails and so on that maybe you have seen. So today's presentation is given by Martina Caruso. Martina is a PhD student at IUSS Pavia.
Gerard, apologies for interrupting you. Just on one note, that the link that was on the email message,
yes,
it's not working. So I don't know if there was some copy and paste error there, and so I needed to add the event to the calendar and then go from the link that is in the calendar.
Yeah, Karim was just mentioning that before.
Okay,
there was something. There is something that is that's happening with those.
No,
links.
I was just wondering if it would be the case of, I don't know, probably now you can't handle it, but it would be the case of sending the message again with the correct link, but maybe not. If you see that there's enough people, that plenty of people have managed to connect, and it means that they probably managed to find the solution.
That's what we were saying at the beginning. There were a few people, but then I could see a big wave of people were coming.
Apologies for interrupting you.
No, not at all. Not at all. In the meantime, while people are maybe figuring it out, we're just giving some introduction. But
now I'll mute myself and I will not interrupt you again. Apologies.
So as I was saying, the presentation is by Martina Caruso. So Martina is a PhD student at IUSS Pavia in the UME program. And Martina's presentation will be on the title of Integrated Economic and Environmental Building Classification and the Optimal Seismic Vulnerability or Energy Efficiency Retrofitting. So quite a long title, but I'm sure it's going to be quite an interesting presentation. So Martina, it's over to you now.
Okay, thank you. You should hear me, right?
Yes.
Okay, so okay, good afternoon, everyone. As Gerard anticipated, I'm a PhD student at IUSS in Pavia, and my presentation today will be about the main research topic of my PhD, which I've been working on with the support of Professor Rui Pigno and with Federica Bianchi, Francesco Cavalieri, and Maria Teresa Lemmo. We will discuss our proposal for a new integrated economic and environmental classification scheme for buildings, and we will give some suggestions on which performance metrics may be used for the identification of optimal renovation strategies for buildings, considering both seismic vulnerability and energy efficiency. So I will start with some motivations. The first one is that the construction sector is the main responsible for environmental impacts due to human activities. Indeed, in Europe, the 40% of carbon emissions is due to buildings. The European Union is also setting more and more ambitious targets in terms of reduction of carbon emissions up to climate neutrality by 2050. So we as building engineers can really make a difference towards the achievement of such targets through the design of new buildings or the retrofitting of the existing building stock. Many procedures do exist in literature that allow the quantification of environmental impacts associated to buildings, considering their entire life cycle from their construction through their operational phase and up to their demolition or end-of-life phase. However, traditional life cycle assessments do not include the contributions of potential earthquakes or even potential hazards in general. But when we describe a strong seismic event, we are used to describe it through the number of deaths or injured people, homeless people, or by the economic losses that are associated to post-earthquake retrofitting activities, or to business inactivity also. However, we cannot anymore neglect the fact that post-earthquake retrofitting activities do produce also environmental impacts. And those contributions should be included into traditional life cycle assessment. To do so, we have several methods that allow the conversion of buildings components damage into environmental impacts, so that we can use environmental impacts as decision variable within traditional loss assessment methods. Lastly, there is a need for a methodological framework for integrated assessments of buildings that consider multiple performances of the building itself. In our discussion, we will include, for example, both seismic and energy performances, and also for impact evaluation metrics that are meaningful for the identification of optimal retrofitting strategies. So I will start with a brief overview of the life cycle framework that we developed. That is, of course, based on the existing life cycle analysis and life cycle cost analysis procedures, but it includes the contribution of potential earthquakes also. So the first life cycle stage that we consider usually for buildings is the construction process, which usually includes raw material extraction, transportation of those materials to the factory, and the installation process within the construction site. Then we can move to the operational phase of the building, which is the phase in which people and occupants use the building. We will define several sub-phases within the operational phase. The first one is the use phase before a retrofitting intervention is made in the building. In this operational phase, we will, as I previously mentioned, we will consider the contribution of potential earthquakes in terms of average annual loss, what we called AAL, due to seismic hazard, and the energy consumption of the building. Then we may need to do a retrofitting intervention on the building that may be or not consequent to an earthquake occurrence. In that case, we should, of course, consider both post-earthquake repair activities and retrofitting intervention. Concerning retrofitting interventions, we may have sole seismic strengthening or energy efficiency refurbishments only, or even integrated interventions that are aimed at reducing both seismic vulnerability and energy consumption. So the next step is the estimation of average annual losses and energy consumption, considering the effectiveness of the retrofitting intervention adopted for the building. Lastly, we have the demolition phase, which is the end-of-life stage of the building, in which we considered the demolition of both construction and retrofitting materials. So wrapping up, we will have a big summation of the contributions of each of those stages that we, in terms of life cycle performance metric, or LCPM, that we decided to use as performance metrics, costs in euros, and environmental impacts in terms of equivalent carbon dioxide. All those contributions, as you can see, are normalized, just to be more general, by the total floor area and the total service life of the building. This summation, this kind of evaluation may be useful when we are dealing with, we are comparing different buildings that belong to different buildings typology, for example, concrete, masonry, or steel, or whatever, or maybe a newer building compared to existing ones. But if we deal with just a single building, we can focus to the only on the post-retrofit stages, because the pre-retrofit ones are of course the same for a single building. So when we are evaluating which retrofitting option is the best one for a building, we can imagine to introduce a new integrated classification, which is based on post-retrofit annual costs and emissions, estimated as we previously discussed, which is of course inspired by the already existing energy and seismic risk classification schemes. But it is quite different because for two main reasons. The first one is of course related to the performance metrics that are used as a basis for the classes, which are again costs and emissions. And because we are considering seismic and energy performances together in an integrated manner. So here, now I want just to do an hypothetical example for a building located in central Italy. Assume we have calculated post-retrofit costs and emissions for the as-built configuration, and that we get a class D. Now we want to design a retrofitting intervention for this building. We can try with a seismic strengthening only, or with a sole energy efficiency refurbishment. What we can see here is that a sole seismic strengthening is giving a very high reduction in terms of costs, but a very limited reduction in terms of emissions. On the contrary, the energy refurbishment is giving a very limited reduction of costs, but a very significant reduction in terms of emissions. So what I wanted to say through this example was that in order to guarantee a class upgrade, we would need an integrated reduction of both costs and emissions, and that just the reduction of one of those may not be enough. So considering that central Italy is a region characterized by very high seismic and energy demands, we can also think about an integrated intervention that may guarantee one or even two class upgrades. So to understand better our framework and our proposal for this classification scheme, we will go through the application of the framework to a case study building, which is an existing school building in central Italy, which looks like this. As you can see here, we will go through each step, each life cycle stage, and for each of those, I will provide economic and environmental estimates. So starting from costs, we assumed a 900 euros per meter squared construction cost for this building. Concerning environmental impacts instead, we used a specific method for life cycle assessment, which is called economic input-output method, or and we used a web tool which is available to perform this method and which is referenced in this presentation. So what we need to use this method is an estimate of dollars of expense in a specific construction sector, that in our case is the construction of a school building. The web tool will be able, depending on the quantity of expense in that sector, to give estimates of environmental impacts per $1 million of expense. What we can immediately understand is that this method is quite approximate because it is only based on the assumption that given an expense in a sector, we are able to calculate the corresponding environmental impacts. But it was, we deemed it was fine for our first application, but in the second application we are working on in these days, we decided to perform more accurate life cycle assessment, which is called bill of material life cycle assessment, that consists in the definition of all the components and all the materials within the building to get the corresponding environmental impacts. Another thing I want to say about that is that you see I'm talking about dollars of expense, and that is because the web tool was developed specifically for the US. So we had to introduce some conversion factors to move from euros to dollars. And another thing is related to the environmental impacts that, as you see, are from cradle to consumer. When we perform life cycle assessment, we usually calculate the environmental impacts from cradle to grave. So from construction to demolition for a building. But we can also have intermediate evaluations where we stop at previous stages. In this case, we are limiting our evaluation up to the moment in which the building is given to the consumer. So the occupants are start using the building. And this is fine since we are just dealing with the construction process. So the result is 450 kilos of equivalent carbon dioxide per meter square. Then we can move to the operational phase before the retrofitting intervention is made. And again, here we will estimate the average annual loss due to earthquakes and the energy consumption. Starting from the earthquake loss assessment, we decided to use the FEMA P58 approach. I'm sure most of you are familiar with this approach, so I will not go too much through the details, but I will just describe in general the steps that are part of this approach. The FEMA P58 approach is a fully probabilistic method to estimate losses that are expected in a building given the seismic hazard at the site. So once we know the building and we know the site of interest, we can perform step one, which is the seismic hazard analysis, in which we are mainly answering to the question, how frequently will an event of intensity IM occur in our site? Step two is the structural analysis of the building, for which we need a numerical model for our building, and we need to perform structural analysis that may be nonlinear static procedures or pushover, or nonlinear dynamic analysis. The result of step two are the so-called engineering demand parameters, or EPD, which result in the building due to the occurrence of the event defined at step one. For our application, we used pushover analysis, and we used the N2 method to assess to assess the EDPs at 9 different seismic intensity level. EDPs may be, for example, interstory drift ratios or floor accelerations or velocities. Step 3 is instead damage analysis. At this step, we need to collect an inventory of vulnerable components in our building. In our application, for example, we considered structural reinforced concrete components like beam column joints and masonry non-structural components like external infills or internal partitions. For each component, we need the so-called fragility function that provides the level of damage that is expected in the component given the attainment of the EDPs defined at the previous step. Lastly, step 4 is the loss analysis. For this step, we need instead what we call consequence functions. So for each damage state considered for each component, we know which repair activity we would need to repair our components. So the consequence functions are, for example, in terms of costs or carbon emissions that are produced by the repair activities needed to repair each damage state considered. So the results are finally in terms of loss curve. This is the economic loss curve, and in terms of average annual loss, which was estimated to be around 5,000 euros per year, or in other terms, 0.38% of the replacement cost. Concerning environmental impacts, I want to spend just a few words on how we developed the consequence functions in terms of equivalent carbon dioxide emissions. And so once we had a detailed description of the repair activities needed for each component, we could estimate the quantity of materials needed for each repair activity, and finally use the inventory of carbon and energy database to get our estimate of environmental impact per kilos of material. The results are again in terms of environmental loss curve, and the average annual emissions expected in the building are more or less equal to 2,000 kilos of equivalent carbon emissions per year. Also 0.28% of the replacement impact. Concerning instead the energy performance assessment, we decided to use a software which is called EC700 and which was developed by Edil Klima. So we built our model, and we performed energy calculations in static conditions so that we could estimate the energy needs for the building and the energy class, which in our case was E. For this first application, we just focused on the energy needs for heating the building. Whilst in future applications, we want to include energy needs for cooling, ventilation, illumination, and so on. This was just for the sake of simplicity for the first application. The results are shown here: 27,000 euros per year and 53,000 kilos of equivalent carbon dioxide per year. What you can immediately notice is that there is a difference of about 1 order of magnitude with respect to the estimates of resulting from the earthquake loss assessment. And the reasons we found were mostly two. The first one is related, as you see here, to the specific architectural configuration of the building, which features very large openings along the building vertical envelope. And the second reason is related to the type of analysis we did, which was in static conditions. So we assumed an average temperature value to be constant within the season considered to estimate energy needs for heating the building. So those results may be quite conservative. Again, in our second application, we are trying to perform analysis in dynamic conditions, considering the variation of temperature through a single month, but even within a single day. Then we designed 8 different retrofitting options for this building, including soil seismic strengthening options, soil energy efficiency refurbishments, but also integrated options. The first one is a soil strengthening one because it consists in the strengthening of external beam column joints through the application of steel reinforced polymer or SRP sheets, as you see here. The second option is just an extension of the first one, in the sense that we proposed to extend the application of such sheets all along the external columns and beams. This is not a solution of common practice, but we were interested in including it because we were trying to avoid the formation of thermal bridges due to the material discontinuity over year between SRP and concrete. The third option is instead an integrated option that couples the external joint strengthening with the application of a 2 centimeter thick insulation layer all over the vertical building envelope. The fourth and the fifth options are instead energy efficiency refurbishments. And you see that the first one is a traditional solution for thermal insulation by the application of expanded polystyrene panels or EPS panels, whilst the fifth option is an innovative solution with a 2 millimeter thick application of a ceramic layer all along the building envelope that performs equivalently to an 8 centimeter thick EPS panel. The sixth option includes the introduction of reinforced concrete shear walls, of 4 reinforced concrete shear walls in our building, 2 per principal direction, as you see in plan and in the numerical model. The 7th and the 8th options are integrated options that couple reinforced concrete shear walls with EPS panels and ceramic application, respectively. For each of those retrofitting options, we could estimate both costs and emissions due to the installation process. Then we can move to the use phase after the retrofitting intervention. And it is clear that the results of the earthquake loss assessment and of the energy performance assessment will be influenced by the effectiveness of the different interventions. What we can see, for example, is that concerning seismic performance, the most effective solution that provides the highest reduction of average annual economic and environmental losses is reinforced concrete walls. On the contrary, in terms of costs and emissions of due to energy consumption, the 2 options of thermal insulation, as I previously anticipated, perform equivalently. Finally, we are at the end of life of the building, which is the demolition. For costs and emissions associated to demolition, we just assume them to be equal to 20% of the corresponding estimates for construction and retrofit. And here I'm just reporting such values for construction materials. So those are 20% of the estimates reported in the slide about construction. Now we have our environmental and economic estimates for all the stages we presented, and from the construction up to the demolition. And you can see that this is kind of a linear life cycle for our building that starts here and ends with demolition. However, we know that the demolition of buildings do produce a very large amount of waste, and we cannot imagine today that all this waste would be just transported into landfills and without having any alternative and second options. So what we will do in future applications and developments of the framework will be to move to a circular life cycle, which will include a newer phase, which consists in the reuse and recycle of demolition materials that will be perfectly coherent with the circular economy principles, because we can imagine is that in this way the demolition waste will be reused and recycled and be put again within the market to start a newer life cycle of another building or of another product in general. Another thing I want to say about this is that up to now, we just considered retrofitting options, as you previously saw, that are traditionally used in engineering applications. However, several researchers today, like Passoni et al., are working on more sustainable solutions for retrofitting that are designed in the proper way so that after the demolition of the building, we can completely reuse and recycle those retrofitting materials. And this is one of the best things we can do when we deal with existing buildings, of course. So coming back to our framework, now we have all the contributions we are interested in. Now I will show the results for the as-built configuration and for each retrofitting options. But even if before, as I said, that these evaluations may be useful when comparing different types of buildings, because I already said that the pre-retrofit phases are of course the same for a single building. So I'm presenting these results just for the sake of completeness. If we come back to, if we consider that we are interested in identify the best solution for a single building, that in our case is the school building in central Italy, we can just focus on the post-retrofit stage and use costs and carbon emissions are meaningful performance metrics to select the optimal retrofitting strategy. And we can use as supporting decision variable the payback period of the retrofit investment, which is the time interval that is needed to fully pay back the retrofit investment through the benefits provided by the retrofitting intervention adopted. We calculated the payback period using this equation for the net present value that you see plotted here in those colored lines, each representing a different retrofitting option. The payback period corresponds to the point when those lines reach zero, which is the point where the retrofit investment is fully paid back by this part of the equation, which is related to the benefits produced by the retrofitting adopted. What I want to say about this is that you see that the lowest payback period is the one associated to the blue and the purple lines, representing reinforced concrete walls only, and the integrated intervention with reinforced concrete walls and EPS panels. So we can see they produce almost the same payback period, around 11 or 12 years. However, what's interesting is that if we consider a longer term and we look at the next years after the payback period, we can see that the integrated option performed much better than the other in terms of highest benefits. The second decision variable we can use as support in the selection of the optimal retrofitting strategy is the average annual loss of life due to seismic hazard, because we cannot neglect the fact that earthquakes do have very serious consequences on the society and on the community that are related to life safety and life protection. To do so, we use the casualty model that is included within the FEMA P58 approach, for which we needed, first of all, a population model. What we are interested in here is how many people are expected to be within the building at different hours of the day and at different days. You see here that in a school building, it is very evident which are the times of the day and the days of the week where we have the majority of occupants. What we need, secondly, is the definition of some collapse modes for the building that we defined according to the suggestions of the FEMA P58 guide manual. And finally, for some components, we also defined a fatality rate. So for some components, for example, masonry, infills and partitions, we defined an area which is possibly affected by the collapse of the component itself. We assumed in a conservative way that such area will be equal to the dimension of the masonry, infill or partition, assuming that all the component is transferred into debris after the collapse. And then we assumed a fatality rate equal to 0.9, as suggested by the FEMA P58 guide. So now we can finally look at the results in terms of post-retrofit annual costs and emissions, but also in terms of payback periods, which we normalized by 20 years, which is the time, the post-retrofit life we assumed for our building, and the average annual loss of life, which is instead normalized by the total number of people that are expected within the building. So how do we select the best option? The best option may be the one that produce the highest reduction in terms of costs and emissions if compared to the as-built configuration, and also the one that features the lowest payback period and the lowest average annual loss of life. And what we can see is that the best option for our case is the integrated option with reinforced concrete walls and EPS panels. If we just look at the first plot, one could argue that also thermal insulation only may be considered for this building, because it is kind of resulting in a good reduction of costs and emissions also. And it is also less invasive, much less invasive if compared to the introduction of new reinforced concrete walls. However, if we look at the second plot, it should be immediately clear that the thermal insulation option only is not tackling life safety within the building, whilst the integrated option is providing also a significant reduction of average annual losses. So an improvement in terms of life protection if compared to the as-built configuration. We decided to move our building also in other cities to see how the results could change. We selected 2 cities, Reggio Calabria and Cuneo, because we were interested in varying climatic and seismic conditions to see how the results would change. And here is what we got. From those plots, we can see the different effectiveness of the different options in the 3 cities. But what is much more evident is the increasing trend of costs and emissions for increasing energy needs over year, because Cuneo is the city with the coldest weather if compared to the other 2. So this is maybe again due to the specific configuration of the building we are studying here. In the second application we are working on now, we are getting comparable results in terms of earthquake, seismic and energy performance assessments. So maybe we are expecting quite different trends if compared to those. So now I will just focus on some of the results presented in the previous slide, considering the city, the building located in Cuneo, because they are quite interesting, as you will see. The results are superimposed on the potential classification scheme we are proposing. And what we can see, for example, for the joint strengthening option only, we see that there is not an improvement in terms of costs and emissions if compared to the as-built configuration. And this is maybe due to the fact that this kind of option is quite costly and carbon emitting, especially in a region with these characteristics. So without high energy demands for heating and lower seismic demands. Instead, what is interesting next is that if we plot the results for the thermal insulation only and for the integrated option with concrete walls and EPS panels, we can see that the results are almost coincident. And that is again due to the specific characteristics of the city of Cuneo, because thermal insulation only is strongly reducing costs and impacts at the same way like the integrated option. However, if we recalled what we previously said about the average annual loss of life, we can again consider the optimal solution as the integrated one, since it also tackles life protection. You can see that here I did not put any value ranges, and this was done on purpose because we have not enough data to properly define such value ranges. To do so, we would need a much more extensive parametric study on multiple buildings and also multiple buildings typologies. So now I'm at the end of the presentation. I will draw some conclusions. The first one is that the framework is readily applicable to any kind of building, any building typology, and it can be used as a basis for a new integrated classification for buildings, which is based on a life cycle economic and environmental impacts, and that integrates seismic vulnerability and energy efficiency for buildings. And hopefully it can go beyond the currently independent energy and seismic classification systems. In addition, we tried to demonstrate that expenses, monetary expenses and equivalent carbon emissions can be meaningful performance metrics for the identification of optimal renovation strategies for buildings, together with the payback period of the retrofit investment and the average annual loss of life due to potential earthquakes. Then integrated renovation strategies are always convenient, especially in long-term evaluations in terms of long-term benefits. And lastly, the geographic location can really influence the results, the economic and environmental evaluations. It is therefore possible that the definition of value ranges for the integrated classes we were presenting before might vary from one location to another, as it is done in the energy classification scheme, for example. Lastly, just a glance to some future outlooks. In the second and further applications of our framework, we want to introduce the indirect losses, which are namely those associated to partial or total interruption of business activities within the building, translating those losses into economic contributions to the average annual loss. The consideration of demolition and reconstruction according to up-to-date seismic and energy requirements as an alternative to retrofitting, in the sense that generally, maybe we will prove that demolition is not a sustainable solution most of the times, but maybe we can have situations where demolition should be preferred if compared to retrofitting for specific buildings. As previously discussed, energy performance assessment in dynamic conditions that account for the variability of outside temperature during a single day or during an entire month. And finally, the extension of the application of the framework to a group of buildings, of existing buildings, in order to further explore the potentials of the method and of the classification we discussed. So I'm at the end. Thank you very much for your attention. Now, if you have questions or doubts, I'm happy to answer. I will be happy to answer.
Okay, thank you very much, Martina, for a very nice presentation. So, do we have any questions or comments from anybody attending? I think, as usual, I think I will have to. Karim, yes.
Hi, Martina. Thanks a lot for the presentation. I just want to ask you about the economic input-output method. I mean, you mentioned that it is specifically for the US, but that you apply sort of conversion to make it fit to what you are calculating in your study. Could you please tell me more about this conversion?
Yes, just a second, because I'm coming back to, okay, here. Yes, I just used a conversion factor to translate the expense that we had in euros into dollars, using the commonly conversion factors from euros to dollars. And another thing we did is actually about related to the year reference of the web tool, because in this specific web tool, the expenses were referred to 2011. So we had also to include a conversion factor of dollars from 2011 to 2021, which was approximately equal to 1.4 more or less.
Okay, so you did the first currency exchange from dollars to euros, and then you accounted for the time effects on the money because there are interest rates and so on. going
yes,
from 2000?
The data within the Web 2 were available for 2011.
Yeah, okay, thanks a lot.
You're welcome.
Okay, thanks, Karim. Okay, I was going to ask you just a quick comment about related to what you were showing here, Martina. So in the case of seismic loss estimation, so you mentioned the FEMA P58 and which is a common method that people use. So there is that method, and then there are some simplified methods to do loss estimation if somebody doesn't want to implement each one of these 4 steps in a lot of detail, so that they can get maybe a quick answer, but not a bad one. In the case of the environmental loss estimation, or the assessment you were showing then, so you mentioned the environmental input-output method. So were there any other methods that could maybe be more simplified to make that more accessible, or did you look at anything else, and what would, like, let's say, the options in that side of things?
Okay, first of all, I want to say thank you, because I forgot to say that, of course, anyone could perform the calculations within each module in the way they prefer. So here I decided to apply the FEMA P58, but anybody can use other methods. Concerning environmental impacts, I wrote something here. We tried to calculate the consequence functions in terms of environmental impacts, both in terms using the EIO method, as we discussed for construction, but the final consequence functions we used within the calculation were those I'm explaining here. So once we know the repair activity, we gave a rough estimate of the quantity of materials needed to perform this activity. So I started from the fragility functions and the definition of repair activities given by Cardone et al. For reinforced concrete and masonry components. So I tried to calculate how much concrete or clay bricks I would need to perform the repair activity. And then I used this database, which is called Inventory of Carbon and Energy database, which is available fully free in the internet, and which reports several data of environmental impacts for materials. So you will see kilos of equivalent carbon dioxide per kilos of material. And this is good, I think, because it collects data specifically for the European region. So I was happier to use this method rather than the other one because it was more specific for Europe. I hope I answered to.
No, sure. Exactly what I was hoping to hear.
So I think even using other methods, you can just write consequence functions in the same way, just using another way to calculate average annual loss.
Sure. Okay. Does anybody else have any question or comment? Cannot see everybody. If not, I was going to ask something. It's more of a small thing that I noticed toward the end of your presentation when you were looking at the application of a retrofit in Cuneo. Mm-hmm. So if I'm not mistaken, the point you showed, actually by performing the retrofitting, the performance was worse both in terms of the environmental, yes, this plot. So you actually, so the first version of it with just 2 points, so the annual costs increase and the annual emissions decrease. So actually you were in a better position by doing nothing.
Yes, and this is because the joint strengthening option, the installation of this retrofitting in the city of Cuneo would be maybe too costly and too carbon emitting. It is not effective in the case of Cuneo. If we were in Reggio Calabria, maybe, surely that point will be over here somewhere.
Okay.
So that's the answer we found for this.
Sure. Oh, that's quite interesting.
And this is also interesting because the thermal insulation is just giving the same result of the integrated option just because Cuneo has a low level of seismic hazard whilst higher demands of energy for heating.
Mm-hmm. And in terms of those retrofitting solutions, so you mentioned, this is a very vague question, I realize. So in terms of the retrofitting solutions that you mentioned, you were describing how you explored some options in terms of seismic ones, and then some environmental ones, and then some hybrid ones. So in terms of seismic ones, I think many of the people who are maybe listening now would be familiar with what they are. And in terms of the environmental ones, or those kinds of ones, also some options will be available. But for the hybrid ones, is there any kind of guideline in terms of, or indication or way of knowing which one would be a good combination of both, or is it just something you need to try and see for yourself with these kinds of assessments?
Okay, for the first application, we decided to use a very traditional energy efficiency refurbishment. Maybe it is the most well-known because it's just insulation of the building vertical envelope. So we, thanks to Maria Teresa, who works with, which is an energy efficiency practitioner, she suggested such retrofitting option for the specificity of our case study. For example, for the other application I'm mentioning quite a lot of times, which is a residential option, a residential building that has a specific external configuration. Thermal insulation with panels is not possible. So we are exploring different solutions to reduce the energy consumption in another way. But the choice we made here was just using a traditional method for dealing with the reduction of energy consumption.
Okay. So last chance, any question or comment? I'm out of questions and comments, so this is it now. Okay, I don't see anybody raising their hand. So if there's nothing else, I would just like to say thanks again to Martina for a very nice presentation. So I think it's very, very nice to see things like this, and also some unexpected results, and surely of interest. As I was saying before, this seminar it was being recorded, so if you want to see anything again, it will be available online and so on. So there should be no problem there. And the last thing is that we should be having another one of these seminars in a few more weeks, possibly towards the end of July. You will get a notification, and the general spam I do be sending, I send to you guys shortly with the announcement for that. So so again, just thanks to Martina, and I guess we'll see you all in a couple of weeks' time. Okay.
Thank you.
Thank you. Bye bye to everyone.
Thank you.